name is Curtis Brown, and I have with me Tom Dick and Steve Kokoska. Really excited to have those two guys here tonight. We are getting acclimated with accumulation tonight. We've got a bunch of accumulation problems. They've been accumulating over a period of time. And we are. Steve Kokoska, really oh man, I can hear myself here. We are ready to get things going. So, Steve, I think I'm going to turn it over to you.
Okay, I'm going to give it a shot. Here we go. Oh, you got to let me,
Oh, I have to allow you to
yeah,
present.
you have to let me do that. Sorry about that, Curtis.
You got it.
All right, let's try this and see if it works. Here, let me see if I can find this. There we go. Okay, how's that, Curtis? Can you
You're
see
on,
that?
You're on, sir.
All right, great to be back with you and Tom again. We do have some great problems tonight. I really do enjoy these applied problems. I don't know why, but this is one of my favorite sections in all of calculus. Still remember learning about this as an undergrad at Boston College, and for whatever reason, my undergrad teacher was extremely enthusiastic about this stuff, and a lot of it rubbed off on me. I really do enjoy it. So let's start out with kind of a classic problem here where we want to take a look at a region bounded by the graphs of these two expressions, these two functions, and we want to find the area of the region bounded by those two graphs. So first of all, we have a trigonometric function over here. We have a sine function. I think that has period, let me think about that for a second, 2 pi divided by pi. So it has a period of 2. The second function over here is a quadratic. So we know the graph of that function is a parabola. We know that it opens down because there's a negative coefficient on that x squared term. And so I produced a graph here. Some people, or I frequently get asked, how do I produce my graphs? And I generally use Mathematic here if I'm not using the Nspire. And I hope you can see some of the colors there, Curtis. This kind of looks kind of nice. The parabola is up top here in green, and the sine function is down below. And when I first graphed these two, I said, you know, it sure looks like these two graphs intersect at x equal 1 and x equal 2, but I just wanted to double check that. So I don't think I could really take 4 sine pi x and set it equal to the other expression and solve, at least analytically, with a piece of paper and a pencil, but I do know that the sine of pi is 0, the sine of 2 pi is 0, and I was able to factor this quadratic, and it has two linear terms, x minus 1 and x minus 2, so indeed, they do intersect here at x equal 1 and x equal 2. Now, when I looked at this kind of quickly, I thought, well, you know, maybe we could just find the area of the region up in the top and double it, and that's not quite right. Although it might look like on this graph there's some symmetry, there really isn't because the top is a quadratic, the bottom is a trigonometric function. So they might look like, or it might look like, there's the same amount of area up top as the bottom, but it's not quite true. So a way that I think about this is I have to identify the high curve, what I call y sub high, and the low curve, which I call y sub L. And again, when I was doing this, I thought, well, you know, this seems like it might be a good candidate for the calculator to compute this definite integral. But let's take a look at this. It's going to be the definite integral from 1 to 2 in order to figure out the area of this region. There's my y sub high curve. There's my y sub low curve. And I stared at that for a minute and said, hey, son of a gun, I think I can actually find an antiderivative. I can integrate term by term. So don't let me make a mistake on this one, Curtis. I'm going to arrow up just a little bit here. There we go. Hey, that's working tonight. How about that? So I find a antiderivative, or I integrate term by term. There's my minus 16 over, or 16 times x cubed over 3, 48x squared over 2. Yeah, a little simplification, minus 32x. To go from here, this is really a pretty straightforward U substitution, so I didn't put that in there explicitly. And then theoretically, all I need to do is to plug in the upper bound and to plug in the lower bound and do a little bit of subtraction. And I did that, and that's kind of neat to see. There's the exact symbolic answer, 8 thirds plus 8 divided by pi. Now I'm going to show you a little bit with the calculator in a minute, but here's another part to this question that you could try tomorrow morning at 8 o'clock. You know, it sure looks like the top region up here and this bottom region down there sure looks like they're equal in area. What's the difference in area and which one is bigger? So see if you can try that one for 8 o'clock tomorrow morning. Good. I wanted to check a little bit of this with the calculator, and Tom will do a little bit with the TI-84 in a minute, but you know I like to use the TI-Nspire. And so I was able to produce a pretty nice graph on the left-hand side using the TI-Nspire. That shaded in region between 1 and 2. That's the region R, and that's the region I'd like to find the area of. And I did that, and on the graph screen, I got a 5.213, which I believe is that symbolic answer that we got a minute ago, 8/3 plus 8 divided by pi. And I wanted to check this on a calculator screen. Here's my function f. I can define that on the TI-Nspire. Here's my function g. And I can just do a definite integral right there on the calculator screen. And this is just too cool. It comes back with the exact symbolic answer. Is that my answer? I better check that here. I don't know if I did or not. Let's see. I'm going to multiply that out. That's 8 pi plus what? 24 divided by 3 pi. Let's see. That's equal to 8 pi divided by 3 pi with two separate fractions plus 24 over 3 pi. Is this working out? Yeah, there's my 8/3.
There's
And
your
there's
eight
my,
thirds.
yep, there's my 8 over pi. So yes, it is indeed the exact symbolic answer that I got on the previous page. Pretty cool. One thing, maybe Tom will dwell on this a little bit more, but one thing I wanted to mention, I'm going to sneak back to page 1 for a moment, and I want to look at this original integral right here. You know, on problems like this, where students have to find the area bounded by a curve up above a high curve and a low curve, you know, there are a couple of different ways that we can actually write this definite integral and have and arrive at the correct answer. For example, some students may write this as the definite integral 1 to 2 of YL, the low curve, minus the high curve. I believe that some students are taught to just, well, subtract the two curves, and if you end up with a negative answer, put an arrow and write the positive answer. Well, okay, I teach my students to identify the high curve and to identify the low curve. I think that's a better process. I think that's a better technique to solve these problems. But be careful. If you do y low minus y high and you arrive at a negative answer, you can't just say equals and then put the positive answer. That's an example of linkage, equating two things with equal signs that are not equal. So I think the best way to solve this problem is to correctly identify the high curve, correctly identify the low curve, and set up this definite integral correctly. Cool. Let's try B. So in B, I've got these two functions. I've got 3 divided by 1 plus x to the 4th. And I've got y is equal to, what is that? E to the tangent inverse of x. Holy Toledo. Well, I have very little hope of doing this one analytically, I think. There's a graph of these two functions. There's the region R. And this is going to be my high curve, y sub h. This is going to be my low curve, y sub L. And one of the very first things that I'm going to have to do in this problem is I'm going to have to find these points of intersection. And this is kind of a classic problem on the free response portion of the exam. If you have to find the area bounded by two curves and it's calculator active, one of the very first things you probably will have to do is to find the points of intersection. Tom, correct me if I'm wrong. I think last year one of the points of intersection was given and was nice, was an integer like 0 or 1. But the other one you actually had to find, I think, was a point of intersection that had to be found with the calculator, if I remember correctly.
That rings a bell. Yeah.
Yeah, sound familiar?
Yeah.
Okay. Okay, so here's my first function. I'll define it to be f. That's my high curve. I'm going to add in a little bit more notation for my own benefit. There's the low curve. And if you've been following along with us, I like to use the zeros command because it will put these values in a list that I can refer to, that I can draw from. I can actually extract a value from that list. So find the zeros, f of x minus g of x, find the values that make that zero. There are two places or two values of x. And I'm going to let A be equal to the first element in that list Z, B be equal to the second element in that list Z. Now notice that I have my calculator set to fix 3. So we're seeing 3 digits to the right of the decimal rounded, but don't forget that these values are stored to the greatest degree of accuracy allowed by this TI-Nspire. And so in order to finish this one off, all I need to do is to find this definite integral and notice that I can do this symbolically. I can use the A and B because they're defined over here. And I get a 3.265. Pretty cool. Almost looks bigger than that on the screen, but not quite. And let me see if I can arrow up just a little bit because I wanted to make 2 more comments about this problem. You can also find this answer on the graph screen. A lot of our students feel more comfortable and they're visual, and so they like to solve this kind of a problem on the graph screen. So there I have found this area 3.265 on the graph screen. I am still going to have to find those points of intersection, find the x values of those points of intersection, but I got the same answer on the graph screen. And on the left-hand side, I just wanted to write a little bit here and remind you that if this were a problem on the calculus on the free response portion of the exam, and if f and g are defined, I apologize, I didn't define them way up in the statement of the problem, but if the functions f and g are defined, that's all you would have to write in this problem to receive full credit. Now, you'd probably have to identify A and B. I take that back. You'd probably have to identify A and B, give me some idea of those values. And in fact, I think, Tom, there might be a preliminary part to this question that would say find the points of intersection or find the X values of the points of intersection. But
Pardon,
when,
the question that I was referring to in the chat, I think,
yes,
asked for one of the intersections. They were given the other one.
they were given the other one. Okay. But I think one of the points I wanted to make about this is if the functions f and g are given in the problem, if the functions are named, you don't have to rewrite them here. And in fact, if you do try to rewrite them, you run the danger of making a copy error, missing a parenthesis somewhere. And if you do that, even if you end up with the correct answer, 3.265, you will not receive full credit. You will not have earned all of the points. So that's kind of a test-taking tip, but I think that's important, especially under the pressure of a timed exam. You don't want to waste your time trying to copy those functions exactly, making sure you have all the parentheses correct, the exponents, the denominators. This is much more straightforward. Fantastic. Tom, is that it on number 1? I think it is, isn't it? Yeah.
Yeah.
You want to try a little technology?
Sure. Sounds great,
Okay.
Steve.
Fantastic. That worked? There we go.
Let me try to pull up my TI-84 here. And that problem you just did, the second part of number 1, boy, it's so typical of a problem that we would see on the AP exam, especially
Yeah.
in the calculator active part of
Yep.
that exam. And so it's a good one to kind of illustrate some best calculator practice, much of which you've already alluded to. But I thought I would just kind of run through that on the 84.
Please.
First of all, it's quite likely that the graphs of those two functions might be provided in the stem of the problem. nevertheless, to get them stored away would be a good thing to do, as well as it's a way to check that the graph seems realistic. So I'm going to go ahead and enter those two functions, the 3 over 1 plus x to the 4th. Go. And for my second function, I think we've got the e
Yes.
raised to the inverse tangent.
Yes.
Wild function here. There we go. Of that. Okay. So there we go. Got those two entered. And now I'm just going to do my favorite kind of default window is just a zoom decimal. So I'm going to try that. Yep. Looks like your scaling was a little bit different on your axes. So, but yeah, I'm convinced that it looks, and it's a kind of amazing how flat that that one curve is. Very, very flat near x equals 0, isn't it? It shows up on yours too.
Yeah.
All right, so we're going to try to find the area between these two curves. And so I need these two intersection points, the x values of those two intersection points. So let me go to calc. And we want to calculate an intersection. So let me go down there to number 5. And the first curve, well, I'm on it already. And the second curve, there's only one other, so that's good. Okay. And as a guess, I want to get at least in the vicinity of that first intersection point. So that looks reasonably close. And then when I hit enter, it'll home in on it. And then here's that intersection point to several digits of accuracy here. Now, I want to use that as my lower limit of integration. And so just want to point out that x, that it says x equal, that actually is stored right now in the variable x. So if I was to quit the graph screen and just put in x, there's that value right there. And what I want to do before it gets away from me is I'm going to go ahead and store that as a. Now, on the exam itself, what I would suggest to students of going through exactly this procedure is they would literally then write down on their paper, hey, I'm going to call a equal to this number and write it out to at least 3 digits, but you want to use it to as many digits as possible. Because if it wasn't asked for specifically, if you round it prematurely and use it for a limit of integration, you might end up losing enough accuracy to be off a little bit. Okay, so we're just going to repeat that now, go back to the graph and calculate that other intersection point. Oop, there we go, intersect. First curve, still the blue one. Second curve, still the red one. And now let me go over near that second intersection point. Okay. There it is to its accuracy, or to quite a bit of accuracy. And then when I quit, if I pull up X, there it is. Okay. And now we just want to go ahead and store that in B. Great. And now, finally, we want to go ahead and calculate that area. So I'm going to go ahead and go to the math menu. And what's nice is I've got both my functions stored away, the formulas for them, as well as those two intersection points. So if I pull up that integral template, I can actually put in A and B as my limits of integration. And I want to assure folks that if, as a student, if you write down, look, I'm saying A is equal to this number, negative 1.64 and so on, and I'm calling B this other number, then you're certainly refer to those as A and B later on. The readers will understand exactly what you meant by that. And I'm going to go ahead and pull up Y variables and pull out Y1. I'm going to use good form here. I'm going to put Y1 of X, even though it's technically, I think you can get away without putting that in. But let's go ahead and do good form here. And then our second function was Y2. And if these functions were named already as f and g, I would use those in what I wrote down. If they weren't, you could actually write down, okay, I'm going to call y1 of x equal to this formula, y2 of x equal to this formula, and then again, refer to them in this way.
Tom, am I ever going to get you trained to use those shortcuts for alpha and F4 to get the Y1 and Y2s?
Yes, you actually have trained me to do that, Curtis, but you know, I do like to illustrate that. You know,
Just wondering. I don't know.
So, and
Hey,
there we
perfect.
go. And I hope that looks like the answer we were after, 3.2.
Tom,
Yes, sir.
would you go back to the graph screen just for a
Yeah.
second? Just two things I wanted to point out here. So if you look at those two graphs quickly, and specifically over in the first quadrant, this is a common error, I believe. Correct me if I'm wrong, but some students will look at that and say, oh, those graphs intersect at x equal 1.
Yeah.
Right. We've seen that frequently, is that a student will not go through the process of actually finding that point of intersection, just assuming because it looks like that, oh, it must be 1.
Mhm.
So be careful of that. And if it's possible, Tom, could you try on this screen? Can you do a second in calc?
Sure. And before I do
Oh, I'm
that,
sorry. Go ahead.
let me go ahead and trace
Okay.
over. Well, it kind of skips over that intersection point. But what I was going to say, it's related to what you were saying. It's a little more accurate than eyeballing, but if you trace visually over to where you think the intersection point is, you may not be as close as you need to be. That's
Yeah.
why you really want to use that calculation of the intersection. Yes.
So why is it giving you R and theta there?
I was just going to
Oh my
ask.
God. I must be in polar mode or something. I apologize. I think I was,
You may
let
have
me,
no, go to
it's
format.
format. Is that,
Yeah, go to the
oh
format.
yeah, I'm sorry. I was looking.
I think you inadvertently changed that polar grid.
Okay.
Polar graph.
Well, it actually wasn't inadvertent. I'd gotten a question from someone we know. And I was looking at it recently. All right, let's go back to the graph. Let me
There we go.
trace again. That looks a little better.
That
There
looks better. Yep, there we
But for
go.
example, if I went to here and say, oh, it looks like I'm on it, and I used x equals 0.8 as my
Yeah, right.
yeah, that's just not close enough, right? It was
Yep.
0.83 something. So,
So one of the
yes, your question was go to the calc menu,
yeah,
right?
if you go no, not yeah, right. And if you do let's try option number 7. I didn't really realize this is an option, but go to option 7. You can actually type in a lower limit, and I think you can actually say alpha A right here.
Well, let's give it a shot. So,
You sure can.
A.
Oh, sorry. Spoiler alert.
Yeah, and the upper limit you can just type in now an alpha B. And son of a gun.
Now that's the area underneath that first curve.
That's the area under the first curve, right?
Right.
You would
Right.
have to define as a Y3,
Y1 minus Y2.
Y1 minus
Exactly.
Y2.
Gotcha.
Because you do know that Y1 is greater than Y2 in this case, you could do that,
But that's
right?
kind of cool that you can actually use your stored variables on that graph screen. I like that.
Right.
And what Curtis was just suggesting actually kind of correlates more with the technique you use, Steve. You actually found the zeros of f of x minus g of x.
Mm-hmm.
So here we could have done in y3, we could have done, what was that again, Curtis? F4?
Alpha F4.
Alpha F4.
Alpha trace will get you those variables.
Okay. So let me go to y. Whoops. Let me put here. So if I go to y equals,
Yep.
and I want to pull up y1, I could do alpha F4. There we go. minus, and then alpha F4, number 2, Y2. And now that black graph is the one that we're really after.
Right.
And then we could calculate, like you said, Steve, the integral.
Okay.
And let's see, now I want to make sure I'm on that black curve.
Oh, right. Okay.
Oh, okay, there we go. Y1 minus Y2, that's the one I want to be on. And now I could put in the alpha A.
Okay.
And the alpha B.
How about that?
There's that answer that we got.
Yeah, that's cool.
And it's shade. The thing is, it's not the shading, this region that we're seeing that's shaded black, it's interesting. It's got a different shape to it than the area between the two curves, but it has exactly the same area as the area between the two curves.
Yeah.
And that's because each cross section vertically is exactly the same between the two figures. It's kind of interesting. Okay.
And Curtis, here's a question for you and others. Maybe you can get some people to help you. Tom made an interesting observation here. You know, the graph really looks flat near x equals 0. It almost looks like it's a horizontal line there.
That blue graph, yeah.
Right, the blue graph. Thanks, Tom. Yeah, the blue graph. And so the question is why?
Mm-hmm.
Why does it look like that?
Right.
And I'll try number 2, Tom.
Yes. Yeah. So let me stop the share and turn it back over to you, Steve.
All right, here we go. Beautiful. Okay, so this is kind of a neat problem because I think this is also typical of many of the pre-response questions we've seen recently, which I might call a rate in, rate out problem. So there's a leak in an underground pipe, and it results in pollutant accumulating in a reservoir at that rate, given by that function P of T. It looks awfully complicated. And so my first thought is I don't think I'm going to be able to find an antiderivative of that. And so one of the very first things I might do is to spend the time to carefully type that into my calculator, whether it's an Nspire or the TI-84. So that's a rate function. So it's leaking into the reservoir or accumulating in the reservoir at that rate. What is it in gallons per hour over a 36-hour interval? But starting at 12 hours, somebody has recognized this. Oh my goodness, the reservoir is being polluted. We're going to introduce a cleansing product that somehow attaches itself to this pollutant. And that's being pumped into the reservoir at a constant rate of 2 gallons per hour. Okay. Find the total amount of pollutant that accumulates in the reservoir over the time interval 0 to 12 hours. Okay. Well, this is a classic accumulation problem. We have a rate function, and we want to know how much of this has come in from 0 to 12. We simply do a definite integral from 0 to 12 of P of T dt. And so I've defined this function P in my TI-Nspire. Kind of cool that it uses all that pretty print. I like that. It's almost easier to read there than what's written up top. And all I have to do is to find or evaluate this definite integral. I get a 32.252. And in a question like this, on the exam, that's all you'd have to write is that circled expression down below. And notice that my part A does not ask for units, and so the gallons are not necessary. In general, in a problem like this, if it doesn't ask for the units are ignored. But to be on the safe side, I would not add any units at all unless they're called for. So, okay, here we are. We have this pollutant coming in, but son of a gun, the cleansing agent starts taking this pollutant out at T equals 12 hours. So there are many different ways to look at this. Here's a way to do it, and you might consider with your class tomorrow morning another way to do this. I've defined a function C, which is piecewise defined. It is a rate function. And there's nothing going in between 0 and 12, but it's going in or it's taking the pollutant out at 2 gallons per hour for T greater than or equal to 12. So the amount of pollutant in the reservoir at time T is a definite integral from 0 to T of P of X minus C of X. Now you're right, Curtis. There's a couple of different ways that I could look at this. I could write that as a couple of separate definite integrals. But because of the way that I have defined this function C, I believe that this is okay. So I want to find when the amount of pollutant in the reservoir is a maximum. So theoretically now what I need to do is to take the derivative of that function A, and there's the fundamental theorem of calculus. Now I have to be a little careful here. Let's see, can I do that? Yeah, can I take the derivative? Yeah, I've done that correctly. So that's the FTC part 1. So it's P of t minus C of t. So I have to find when is that 0? When is that derivative 0? So we've already seen this one time tonight. I went to my calculator and I defined this function C. I used the built-in function 0 to find, well, where is that difference 0? There are actually 3 places, one at time t equals 0. We would certainly expect that. And there's 2 others, around a 15.7 and a 27.5. Oh, and I apologize, Curtis. Notice at the very end here of this, I used that such that feature. So I've restricted finding the zeros for t between 0 and 36. And I've also defined this function, which is the amount of pollutant in the reservoir, to be this definite integral. One thing that I have found in talks recently is that even teachers were surprised that you can actually evaluate an integral function like this, not only on the Nspire, of course, but also on the TI-84. Perhaps Tom will show us some of that. So, all right, I'm going to use the candidates test here. And what I need to do here is to evaluate this function A at all the critical values and at the endpoints. And I think that's the best procedure to follow here rather than trying to argue, although there are some arguments here that we might be able to use to eliminate some values, but I'm going to use the candidates test. And it's particularly straightforward if I'm using a TI-Nspire or an 84, because I can create my table of values here right on the screen. Now, there's something funny going on in my table of values. Curtis, I'm going to need a little help on this. I know it's a little late, but I'm going to try you on this one. Here's my endpoints. I've got a 0 in here, and there's my 36. I think it was 0 to 36 hours. Here's my 2 critical values that I found from my calculator screen over here. But then there's this funny number 12 in here as a value of t. Why is that 12 in there? Why do I have to evaluate? Why should I evaluate this function A at t equal 12? What's going on there? Any ideas, Curtis, for 25 bonus points?
Sorry, Steve. I was
Monitoring the chat. Yes, I know. Okay.
no, I was on a different chat. Um,
I wonder why we have to include that value of t equal 12 in our candidates test, because it's not over here. It's not a place where that derivative is 0, but I claim that we do have to include that 12. Why is that?
the output at 12.
Maybe someone in our audience can help us with that.
I'm waiting. I missed all of the candidates and what we were working on.
Okay. Well,
I'm waiting.
It will become evident as I arrow
That's
down.
when the cleansing process starts. So it's your initial.
It does start at 12, but that's not quite the right answer.
Well, that's the first bit of help I got here. So
Okay, well, we'll see it when I arrow down. How about that?
fair enough.
So here's my table of values over there on the right-hand calculator screen. There are all the places, all the values of t that I have to evaluate the function A, and I have to figure out what it's asking for. When is the amount of pollutant a maximum? It turns out there's the maximum, 37.832. It occurs at about 27.5 hours. So the maximum amount of pollutant in the reservoir is 37.832 gallons. I'm going to arrow up a little bit, and I'm going to show you a graph of this function A. And what I was able to do is to place some points on that function A and their corresponding y values or the value of A. So there's a TA coordinate there at 3 points.
I got several people now in the chat talking about a jump or a derivative is undefined at that point.
I like that answer. The derivative is undefined at that point. And in fact, you can just about see that in the graph. If I took away the dot there, the point there, it might be a little clearer, but there is indeed a sharp edge there. And so that's a place where the derivative is undefined for A. That's a critical value, and that's a place that I need to check to make sure or to see if that's where the pollutant is a maximum. Now, there are some other ways, of course, Curtis, that you can argue that one could argue. I mean, one could argue that there is pollutant coming into this reservoir from 0 to 12, so I don't really have to worry about 0. So I could check right away at t equal 12, check at t equal, what is it, 15.73 roughly and 27.51. One might also be able to make an argument that this function A is decreasing between 12 and 15, and therefore you wouldn't have to check 15.73. But I would still argue that the candidates test is the safest, best alternative and justification for solving these types of problems. Very cool. Tom, do you want to do anything with this one, or should I go try the next one? You're still on mute?
Yeah, sorry. What do you think, Curtis? Should we?
Let's move on. Let's go to the next one and get a context.
Okay. So there is a part C to this one.
A couple of cool things we can do still.
Okay, so there is a part C to this one. It says, assuming no more pollutant accumulates after time t equal 36 hours, when will the pollutant amount reach 0? Well, in order to do that, I need to figure out how much pollutant is in the tank, or pardon me, in the reservoir at 36 hours. And then I have to solve this equation because I know I'm taking out at 2 gallons per hour. So that's kind of a straightforward one, but in order to solve this, I used my calculator. I got to take roughly another 14 and a half hours to finally clean out this whole reservoir. Okay, so I'm going to take a look at 3, and this is a cool problem. So this is another area problem, but it's got a little bit of a twist to it, and there's a couple of ways that we could solve this, Curtis. I'm going to need a little help on this one. It says find the value of B such that the line y equal B bisects the area under the graph of y equal 1 over x squared for 1 less than or equal to x less than or equal to 4. So here's what I want to do. I got to find the total area underneath that curve between 1 and 4. Okay, bounded above by the graph, below by the x-axis, between x equal 1 and x equal 4. And then I want to find a horizontal line y equal b so that half the area is up here and half the area is down there. Now, there are a couple of ways to do this one. Here is a way that I attacked it. So the first thing I did is I found the total area under the curve. So that's a definite integral from 1 to 4 of 1 over x squared dx. I can find an antiderivative there. Notice that I factored out that minus sign. That's just me to make this a little bit easier. And I think I got exactly a 3/4. So, all right, I'm just going to remind myself that half of that would be 3/8. Okay, good. Now, again, a couple of ways to do this one. Here's a way to do it. What I thought about trying to do, because we don't do this very often, at least on Monday Night Calculus, I thought about having a right curve and a left curve. So an x sub r and an x sub L. So rather than having a high curve and a low curve, we're going to integrate this one with respect to y. So in order to do that, I need to turn around and solve this function for x in terms of y, and I did that. There it is. So let me see if I've got this right now. Okay. That means if I take the right curve, which is y to the minus 1/2, minus the left curve, which is x equal 1, between B and 1, that total area has got to be equal to 3/8, half of the total area under the curve 1 over x squared from 1 to 4. How about that? So, all right, there's a lot going on here, and I won't go through all the details here, but this is a great problem for solving symbolically and with the calculator. I'll show you a little bit of that in a second. I was able to find an antiderivative. I was able to plug in the upper bound of 1 and the lower bound of b, and I ended up with this equation right here. I did a little bit of simplification. Jeepers, I'm trying to find a value of b. Let's see, what did I do here? I brought this b over to the right-hand side. And let's see, what did I do? I multiplied everything by 8 to get to here. I squared everything to get to here. Multiplied out on the right-hand side, collected terms on the left-hand side. Wow, now I got to solve that for b. It was not clear to me that I could factor that easily. So I went to the quadratic formula. I found a couple of answers here. And the positive one, or the one that I need here, I think is this one. And it's a 0.1503. Sorry, I gave you 4 digits there. So you might think about solving this one. You might think about solving this if I wanted to try this with a y high and a y low curve. What's the high curve? Well, it's this one. What's the low curve? It's this one. I think one of the problems is you have to find that x value right there, because we're going to integrate from 1 to that x value. So you have to think a little bit about what that x value would be, but you can set up a definite integral in terms of y high and that y low b, going from 1 to that x value. And you'll still end up with not a complicated, but an expression in b that you'll have to solve. Okay, I think I was able to use my TI-Nspire a little bit to check my answers here. There they are symbolically. And let's take a look at number 4. Is that all right, Tom?
Sure.
Okay, take a look at 4. How are we doing for time? Okay. All right, so let's switch just a little bit and let's take a look at a couple of volume questions. Let's let R be the region bounded by e to the minus x squared and y equals 0 between the lines -1 and +1. So there's my region R. If you can see that on your screen, it's shaded in sort of a light blue. And I want to take that region R and I want to revolve it about the x-axis and find the volume of the resulting solid. So this is kind of a picture on the left-hand side of what's happening. I'm taking that region and revolving it about the x-axis to produce a solid of revolution. On the right-hand side, I've done my best with Mathematica to produce a picture of that solid. And in fact, I think this is part of the solid here because we're using the disk method. There's no hole in this solid. So I think that's what it looks like. And how do we find this? This is going to be pi times a definite integral from -1 to 1. The function e to the minus x squared, quantity squared. I can do a little bit of simplification here. And let's see, I think this integrand becomes this, and I'm going to plug that into my calculator for a 3.758. There are some other ways that we could attack this if you really wanted to. There is some symmetry here for sure. So I could indeed write this as 2 times pi, a definite integral 0 to 1 of that e to the minus x squared quantity squared. That would be fine also. Let me just show you how I got an answer on my TI-Nspire. Pretty straightforward, pretty cool. Here's e to the minus x squared. There's my definite integral that I need to compute. There's my 3.578. That's all there is to it. Very nice. Gee, I wonder why the calculator didn't give me a symbolic answer for this one. This is a CAS machine. is another sort of open question for you, Curtis. We'll leave that for some of our listeners. I wonder why it doesn't give me a symbolic answer for this one. Okay. So this region R is now rotated about the line y equal 1 and find the result, find the volume of that resulting solid. I did my best on the right-hand side, pardon me, on the left-hand side to draw a picture of what we're trying to do. Take that region R and revolve it about this line. This is the line y equal -1. Here's the way that I would do this. Since the axis of revolution is not a bounding curve to the region, what we're going to have to do here is to use the washer method. And for me, what I need to do is to draw in what I call an outer radius and an inner radius. The outer radius and the inner radius are perpendicular to the x-axis, so this is going to be an integral with respect to x. What's the length of that outer radius? Well, it is at a particular x, it is this high curve, e to the minus x squared minus a -1. There's r sub o squared minus the inner radius squared. The inner radius is constant over this interval, -1 to 1. It's just 1, so -1 squared. And I didn't make use of the symmetry here. I'm using a fancy calculator that I know can do this. I don't think it would save me any time or any accuracy. So pi times the definite integral -1 to 1 of the outer radius squared minus the inner radius squared. And I got a 13.143. That's kind of cool. I think I've got a pretty nice figure on the left-hand side, justification for why this is an integral with respect to x. I've drawn in my outer radius, I've drawn in my inner radius. I've got a nice picture on the right-hand side of what this solid might look like, and I'm going to add a little bit on the right in a minute. And I've got this result down there on the bottom calculator screen. Tom, I apologize. I'm still working on this. It's taken me a long time to be able to draw these solids of revolution with Mathematica and trying to learn how to extract the right parametric curves to get this, but I'm getting better at it. But one of the things I'm working on these washer methods is I'd really like this region in here to be all white. I'd like to draw that disk so that it's all white, so that it indicates, that's not part of the solid in this case. There really is a washer in here, or when we slice, you can really see that washer. So I'm working on it. At least it showed up white, but it's got those sort of grid lines in there, which says, well, it's kind of hard to tell. Cool. All right, I'm going to try 5, Tom.
Tom, you'll have to
And
show
then if there's any
that on Inspire.
What's that?
You'll have to show him how to do that on Inspired.
Okay,
Oh, yeah.
that would be cool.
Yeah.
Okay. So let's see if we can find the volume of the solid obtained by rotating the region bounded by these two curves, wholly Toledo about the x-axis. Okay, let's see what we can do here. Okay, so for these two, I'm certainly going to have to find these intersection points. I did that. I have to find the x values of these points of intersection. So I did that on my calculator rather quickly. Here they are using zeros, and here's my A and here's my B. So let's see, I guess this is technically a washer method because the axis of revolution is not really a bounding curve. So perhaps I should have drawn in here, this is an outer radius and this is an inner radius, but the outer radius is just f of x. The inner radius is just g of x. And so this definite integral is just pi times f of x squared minus g of x squared. And I recognize that there's an awful lot of parentheses in that calculator expression, but I think they're all in there that you can see exactly what I'm doing in that expression. It's a 7.081. There's my best guess at what this solid looks like up on the top right-hand side. And yeah, I think that is a white region there because if you look at where those graphs meet up in the top right-hand corner over here, there really isn't any part of that solid right at x equal 1.506, so I think that's correct. Kind of looks a little weird on the right-hand side, but I believe that's right. That's kind of neat. And I think I've got a 6 here, and then I'll hand it over to Tom to finish up with some technology. This is kind of a classic free response question also in an area volume question. We're often asked to find the volume of a solid where we know the cross sections perpendicular to the x or perpendicular to the y-axis. So here we have a function, pardon me, here we have a region bound in the first quadrant bounded by the graphs of those two expressions, those two functions. 4 log x squared minus 2 and y equal x minus 1 squared. So I think I've drawn those in my Mathematica graph over here, and I've got them labeled. So the solid, a solid S has base R, so the base is in the XY plane. And each cross section of this solid perpendicular to the x-axis is a square. I've done my best to draw that in there, Curtis. So what you're supposed to kind of picture is this square coming up from the XY plane. And so what we need to do is to determine, well, what's the area of that cross section? Well, it's the area of a square. So I'm going to scribble a little bit out over here. So I need to find the area of that square at a value of x in the region here, 1.779 to 4.370. I found those 2 points of intersection. And let's see, we know the area of a square is s squared, but what's the side? The side at an arbitrary value x is just that high curve minus the low curve, isn't it? So it's just f of x minus g of x squared. And I think in most of these types of problems on the exam, we see cross sections that are squares. We see cross sections that are semicircles. We see cross sections that are triangles, sometimes equilateral, sometimes a right triangle, with base in the region and height equal to 2 times the base or something like that. Cool. So I defined an area function. There's the area of a cross section at an arbitrary value x. I got to integrate that from A to B, my points of intersection, which I found, and I got a 20.782. Cool. And down at the bottom, Curtis, I did my best to produce what this solid might look like. So I'm in the XY plane here, sort of flat like this, and my solid is coming up from that plane. My cross sections are squared, which I've tried to denote here with sort of a grid of squares. That's not a bad picture of what this solid looks like. That's kind of cool. Tom, I'll turn it over to you to finish off with some technology.
Okay.
Cool.
Okay, I'll just share my TI-84 screen again. And I know we're running short of time, but just kind of review those best practices. This last question that Steve looked at is another one. It'd be kind of a classic type for the calculator or active part of the exam. In the interest of time, I went ahead and entered those 2 functions that Steve had. And if we wanted to graph those, let me take a hint from Steve. I think the window might work well here. I'll go -1 to, well, 6.6 is probably fine.
Yeah.
I'll go from -1 on the Y up to about, how about 15? Just so we get a window where things will show up.
Okay.
Okay, there we go. It looks like
Pretty
a good
cool.
graph. And as I said here, there's a couple of intersection points here that are not going to be at particularly nice decimal values, but we can calculate those by going to our calculate menu, do an intersection, get our 2 curves, and move close to 1 intersection point. And then we'll quit to the calculator screen and quickly call up that X value and store it
Good.
in A. And then we'll repeat the process, go back to the graph, do calculate, intersect number 5, choose our 2 curves. And you know what? Instead of tracing over there, I'll just look 1, 2, 3, 4, somewhere between 4 and 5. Let me just put in 4.5 for my guess. That looks,
Which is a nice feature, Tom. I think
yeah,
that you can do
just so
that.
you don't have to
Yep.
pressing that button. Ah, got pretty close. And then again, we'll quit. Do pull up our X value. Yep, there it is. And then we can store that in alpha B. And then let me look at the graph one more time here. Let's see, my upper graph is actually, you know, it's not going to matter because we're taking the difference squared. It
Yeah.
doesn't matter. So let's get our integral set up and then we'll be off to the races here. So I'll pull up number 9, our integral. And we've conveniently stored these away. Again, I would actually literally on my paper write down, okay, A equals this value, B equals this value, and then I can refer to those in the integral. And then I'm going to get the difference between these 2 functions and square that difference. So let me do y1 minus y2 and we're going to square that quantity. And I'm not using the best form. I really should put of x, but it understands that those are functions of x.
Mm-hmm.
And hopefully,
Hey, how about that?
is that what you got?
Pretty good,
Very
man.
close. Excellent. Okay.
Pretty good.
But Steve, where's the pi? Where
I
is
know. Where did it go?
that?
Yeah,
That turns out to be one of the most common errors
indeed.
that we see on the AP exam. Is this has nothing to do with a solid of revolution, but so many problems involve a pi where you're doing those solids of revolution that students will stick that pi in even when it's not appropriate. So,
Yeah.
all right, back to you, Steve.
I think that's it. That's it, Tom. We got
through
all
all
of
of them.
them.
Wow.
How do you like that? Any questions, Curtis?
Yeah, there was one
Okay.
question.
Okay.
There actually was one question that that came up, and that was if Tom or Steve could do number 6, show that 3D solid for number 6 using the 3D graphing on Inspire.
Hmm.
And I posted a link to an activity for 3D parametric curves because I think that's probably how you'd have to do it on the TI-Nspire to kind of make that work. So I posted a link to that activity to go and explore as an option for how to create those
Okay.
three-dimensional surfaces on the TI-Nspire in 3D graphing. So probably trying to do it on the fly is wouldn't
Not a good idea. Yeah.
Yeah.
wouldn't potentially be a good experience, but there's an activity built right there
Okay.
for that.
It is. It is neat though for teachers to be able to demonstrate those surfaces. Yeah,
Yes, it is.
they wouldn't have necessarily their students generating them, but to illustrate what a volume of revolution.
Right. Being able to demonstrate the volume of revolution and show that.
Solid.
The
Yeah.
other thing that came up was we need to, I think somebody caught an algebra mistake in the solution. So we're gonna
That's possible.
check that before we post it tomorrow.
Okay, deal.
And then last but not least, if you're a teacher and you're still hanging out here, you can always email me. I will put my email in the chat box here, for you can utilize that to reach out to me and get get a certificate for participation in a professional development. So I'm happy to send you that link. Otherwise, we'll post the solutions tomorrow, and we'll see you in about 2 weeks.
Fantastic. Thanks, Curtis.
Thanks,
Thanks.
everyone. I think